Section 2 is about power, intensity of sound. Okay, every sound source has a certain power. Every loudspeaker has a power, 5 watt, 10 watt, 15 watt. So then every sound source also has a power, certain power. For example, this statement I got from one of the problem in your book. Question says that there is a 75-piece orchestra. Yeah, orchestra has 75 instruments. Altogether, they radiate a sound at power 70 watts. Sound source also has power, like just the electrical source, electrical energy. Heaters have power, mechanical power. So every object which emits energy around has a power. Sound sources also has a power. You can increase the power of the sound source. You can decrease the power of the sound source. In fact, by changing the volume, you are doing that. For example, maximum power of your loudspeaker is 25. By changing the volume, you can make it 20. You can make it 15. You can make it, 10. So that you can lower the power of the source. Or there are two identical speakers. One speaker is 5 watt. If just one of them is on, it's 5 watt power. There you put them side by side and open second one, it becomes 10 watt if they are identical. If you use 3 speakers, it becomes 15. If 4 speakers, 20. So as the number of the speaker increases, then the power of the sources which produce the sound increases. And the rate at which energy is transferred. This is the definition of the power. Better to know this. This definition is definition for every type of power, not only for sound power. The rate at which energy is transferred from theater to the room, electric power. Or sound power, also the same. The rate at which energy is transferred. The rate. When it says rate, you are going to divide that quantity by time. You are going to divide which quantity by time? Energy. Energy, delta E. Energy transferred by time, delta T, is equal to power. This is the general power definition of the power for every type of energy, every type of power, including wave power, electrical power, mechanical power, whatever you think. Delta E over delta T is the general definition of power. And every type of power also has the unit watts. Sound power also has a unit of watt. Electrical power, watt. Mechanical power, watt. So in every types of power, they have unit of watt, SI unit. Here is Fiona, sing. Fiona is going to sing now. She will start singing. Normal power she's singing, but slowly she's increasing the power. Even increases the pitch. And at the end, the bird's blown away. So you can increase the power of the sound by increasing the energy. Okay, there are now a loudspeaker with certain power, and there are 2 listeners. But one listener is closer to the other one. Which listener hears the louder sound? Closer one will hear a louder sound than the farther one. But why? How can we explain physically this fact? Why? Closer one hears a louder sound than the farther one. This fact, why a closer person hears a louder sound than the farther one, is explained by the quantity called wave intensity. Wave intensity. Wave intensity means when the waves are closer to each other. If the waves are closer to each other, so then you are going to say that intensity is high. So we are going to talk about, not only here in this chapter 5, we will talk about magnetic field intensity, for example. When the magnetic field lines are closer to each other, so you are going to see that magnetic field intensity is greater. If the magnetic field lines are farther from each other, you are going to say magnetic field intensity is smaller. In 11th grade, maybe you remember about the electric field. From a positive charge, electric field lines are moving away. But when you are moving away from a charge, electric field strength decreases, because when you're moving away from a charge, in separation between the electric field lines getting larger and larger. Here is a source, like a loudspeaker. This source is sending a sound in the form of energy in all directions. We know that sound expands in three-dimensional surface in sphere, is it? In all surface. Now look at this inner sphere. And look at this outer sphere. These are two wavefronts. Which one has a larger surface? Inner one or outer one? Outer one, which means the same power is distributed on a larger surface for the outer one. Same power is distributed on a smaller surface for the inner one. That's why intensity, sound intensity is greater in the inner one, but sound intensity is smaller in the outer one. So that's why we explain that because sound propagates equally in all directions, the power emitted by the source distributed over a larger area as wavefront expands. So area gets bigger and bigger. That's why intensity of the sound gets smaller and smaller. Power is initially distributed on a smaller area. That's why intensity is high. But as this wavefront expands, the area gets larger and larger. And that's why intensity of the sound decreases. That's why you are going to hear the sound weaker, softer when you are away from a source. So as a result, wave intensity of the sound decreases as distance from the source increases. Wave intensity of the sound decreases as distance from the source increases. Now, a definition of wave intensity. Wave intensity is defined as the rate at which energy of a plane wave flows through the area. So it is the rate at which energy is transferred is known as power. In fact, we know about this. This is power. Power divided by area. For a spherical shape, what is area? How can we calculate the area of a sphere? 4 pi r squared. Then I am going to insert in here, instead of area, 4 pi r squared, because sound wave distributed over a spherical surface. Area of a spherical shell is 4 pi r squared. Then if you insert in here 4 pi r squared, you are going to get the equation for calculating sound intensity at a distance of r from the sound source. So wave intensity I of a sound decreases as distance r from the source increases. As r gets bigger, I gets smaller. Even wave intensity of the sound is inversely proportional to square of the distance from the source. This is an inverse square law. As the distance from the source increases, then the intensity decreases, but not proportionally, inversely proportional to square of the separation. All right, let me show two cases. As I said, as the separation, if the distance to the source increases, so in this case, intensity will be smaller. So for this observer in here, because this observer is at a longer, farther distance, r for this one is longer, or that's why wave intensity is smaller. Wave intensity smaller. Wave intensity of this for this one, r is shorter. Wave intensity is greater. Wave intensity I of the sound is inversely proportional to square of the distance. If distance, let me ask a question. If distance is doubled, say that this is r, this is 2r. If distance is doubled, so then in this case, you are going to say that 1 over 2r squared. So it's going to be 1 over square of 2 is 4r squared. Yeah, and it's equal to 1 over 4 times 1 over r squared. Intensity decreases by a factor of 4 or changes by a factor of 1 over. And what about the power? Power is directly proportional. As power of this sound source increases, intensity increases. As power is increasing, intensity is increasing. Yani 5 watt power, 10 watt power. At the same distance, there are two observers. Which one will hear a high intense sound? Of course, wave intensity for this one will be twice of that one, because intensity, sound wave intensity, directly proportional to power. And then continue. Audibility again. We learned that in section 1, audibility of a sound depends on a frequency. Yeah, where we human beings can hear a sound whose frequency is between 20 hertz and 20,000 hertz. Now I'm going to again open an application which will produce a sound for you. How frequency affects the audibility, so which we are going to try to get again. And then if the sound is less than 20 hertz, we say it is infrasonic sound waves, and then greater than 20,000 hertz, it's called ultrasonic sound waves. And the elephants can communicate with infrasonic sound waves, bats, dogs, and dolphins. They hear and even communicate with dogs, not, but bats and dolphins. They can generate high frequency sound waves. I will make a sound. Yeah, this is a sound which is 647 hertz. I will decrease the sound frequency. No, it became not audible. We cannot hear as frequency decreases. But one more thing also affects the audibility. Okay, this, let me increase the volume now a little. This sound is now, let me make 300 hertz. Now I will decrease the volume. And I will decrease the, in fact, the power of the sound. So intensity, I will decrease the intensity. Can you hear now? You can't. But it's audible sound normally. It's 305. So which means the frequency itself, not only the factor which affects the audibility, also power, yani intensity, which arrives your ear, is also important. So now you are going to hear now. I increase the power, I increase the intensity. Sound intensity, wave intensity. So audibility for that depends on two factors, in fact, not only one. One of them is the, of course, frequency. The other one is the wave intensity, which reaches your ear. If a sound reaches your ear at a very low intensity, so you cannot hear that sound even if it is in audible region of the frequency. So then we will say that the audibility of human ear depends on two factors. One of them is, as we studied in section 1, frequency. That sound must be between 20 hertz and 20,000 hertz. Also, wave intensity of the sound which reaches your ear is also important. At intensity, at your ear. If it is high intense sound, enough intense sound, so that you can hear that sound. That's why many years they made maybe researches and then made a diagram. This diagram explaining, in fact, at what frequency and at what intensity a sound can be audible. This diagram is explaining that. So every sound of every different frequency has a different intensity to be audible, known as threshold of hearing. Now this blue curve right here, blue curve in here, represents the threshold of hearing for different sounds. this blue curve just in the diagram represents threshold of hearing of different frequency. For example, let's get a frequency 50 hertz. I want to know what minimum intensity is required for to make that sound audible. Now you are going to use this diagram. Follow. Okay, this is the point which 500 hertz corresponds. What is the intensity? This y-axis is intensity, x-axis the frequency. So what number on the y-axis corresponds to this frequency? That is 1 times 10 to the power of negative 12 watt per meter square, correct? 500 hertz is audible at a minimum intensity, which is 1 times 10 to the power of negative 12 watt per meter square. Let's get another frequency. And if you generate another sound with 200 hertz, at what frequency, at what intensity this sound is audible? Let's follow. So you go to the blue curve. What is the corresponding intensity? At this intensity, you can make 200 hertz sound audible for a human being. Let's check 400 hertz. 400 hertz, and then go to the graph, follow on the intensity axis, which is y. It is between 10 to the power of negative 8 and 10 to the power of negative 10, which is almost maybe 10 to the power of negative 9, is it? Closer to 10 to the power of negative 9. So most probably 10 to the power of negative 9 is watt per meter square can make this sound audible. 50 hertz, choose the sound at 50 hertz. So which intensity, sound intensity, wave intensity can make this sound audible? It is between 10 to the power of negative 6 and 10 to the power of negative 8, which is most probably 10 to the power of negative 7. So that's why every different frequency of sound will have a different minimum intensity to make that audible, known as threshold of hearing. I always expect a question from this diagram. For example, like this. At 200 hertz, which of the following sounds are audible? A, 10 to the power of negative 12. B, 10 to the power of negative 10. C, 10 to the power of negative 6. D, both B and C. So minimum, yes, this is minimum, but this is also audible because it is in here, inside the region of the sound. It's audible. Both B and C are audible. B is minimum intensity, so which can make this sound audible, but you can increase the intensity more than minimum to still audible, even better increase in intensity. Okay, but did you get a thing in here that when frequency decreases, intensity of the audibility increases? Yani at 500 hertz, you can make a sound audible at low intensity, like 10 to the power of negative 12. But for 50 hertz, intensity of the sound must be greater than 10 to the power of negative 12, somewhere between 10 to the power of negative 7, and 10 to the power of negative 7 is greater than 10 to the power of negative 12. So that's why we say that some sounds are audible, can be audible at very high intensities, like 50 hertz. But some sounds can be audible at low intensities, like 500 hertz. The same thing happens on the other side. As frequency is increasing from 5,000, 10,000, 20,000, as you see, intensity also increases. So in here and in here, You need to make the sound very intense to be audible. But just in the middle of the spectrum, we say spectrum of the sound, in the middle, so then as you see, intensity is low. And the softest sounds that can be heard by average human ear occurs at intensity of 10 to the power of negative 12, about 1000 hertz. Yeah, right here. This sound is known as softest sound, which can be audible for human ears. 10 to the power of negative 12 intensity, about 1000 hertz. But if you check that there is some region here, it is in fact much less than this 10 to the power negative 12. Did you say that? This is minimum, this is the softest sound, but here is some sounds can be audible at the lower intensity than 10 to the power negative 12. These people are special people. They can hear, not average person. Some people can hear a sound less than 10 to the power of negative 12. They are not average. They are extraordinary. Sometimes it happens. God creates some people in a different way. I mean, so that's why this curve in here is representing some people, not every people, not average, can also hear a sound less than 10 to the power of negative 12. And also there is a loudest sound, red line. So if there's a softest sound, there must be a loudest sound as well. So red line is representing the loudest sound that human ear can tolerate. Have an intensity of 1 watt per meter square. Yani this line representing a maximum intensity of a sound that human ear can tolerate. It's about 1 watt per meter square, which is known as threshold of pain. Pain must give some idea to you. If you listen a sound greater than that intensity, so you can be deaf. So you shouldn't listen a sound greater intensity, greater than 1 watt per meter square. It is very powerful, so it can cause a sudden damage to your ear. So this red curve is representing threshold of pain. It's almost the same for every frequency. It is very small difference, but we don't care. That's why for every frequency, threshold of pain is the same, which is 1 watt per meter square. And if you look at this graph, as I said, if frequency decreases than 50 hertz or increases more than 5 kilohertz, you should make sound more intense. This sound needs greater intensity to be audible, but between 50 hertz and 5,000 or 6,000 hertz in here, you can hear a sound at a very low intensity. That's why your book writes this statement. Sounds at low frequencies, yani less than 50 hertz, it's going this direction. Or sound at high frequencies greater than 5 kilohertz must be intense, Yani intensity of those sounds must be great, must be big to be heard. But however, sound of frequency between 50 hertz, 500 and 5 kilohertz or 6 kilohertz, just here. So sounds in the middle, we say it's the middle of the spectrum. However, sound in the middle of the spectrum are audible at lower intensities. So as you see, it's about in here, it's about 10 to the power of negative 12. Exposure to a sound above the threshold of pain, which is 1 watt per meter square, can cause immediate damage to ear, even if no pain is felt. Prolonged exposure means you are listening to music 1 hour, 2 hours, 3 hours without stopping. Prolonged exposure means that. So prolonged exposure to a sound of lower intensity than what 1 watt per meter square can also damage the ear. That's why it's better to make some breaks when you are listening to music. Maybe after 1 hour, so stop and then let your ear to relax, and then 10 minutes, maybe 20 minutes, then go on if you are listening high intense sounds. So for that reason, many rock musicians earplugs during their performance. Rock musics are really loud. So you see the earplug in here. He is eating that putting inside his ear, and then to decrease the sound intensity arrive in his ear.